Next problem up, I'm looking at problem number 20, and if I want to integrate this problem, I could start right away by saying, well, hey, let x equal tan of theta dx, and again, there's something that I'm not seeing, but it's okay, sometimes that happens. Secant squared of theta d theta. I'm just warning you to really pay attention to the u sub every time. So, x dx, and again, this is the long way, but it does happen sometimes. That is the integral of tangent of theta over square root of 1 plus tan. Isn't that secant squared? And the root of secant squared is secant of theta. So that's secant squared of theta d theta. This cancels one of those. The integral of secant of theta tan of theta d theta is secant of theta plus c. And if I draw my triangle, tangent equals the opposite over adjacent. This is square root of 1 plus x squared. So secant is the hypotenuse over the adjacent. There. Now somebody might look at this and say, wait a minute, why are you doing all of that? Couldn't you have just, and the answer is yes, you could have just. Couldn't you have just used a u sub? Can't you say, and again, a u sub is something you should try on every problem, no exceptions. Couldn't you have said, let u equal 1 plus x squared, du is 2x dx? Couldn't you say, this is your u, this is your du, with a 1/2? Isn't that 1/2 the integral of u to the negative 1/2 du? Add 1 to the power, divide by that. Wouldn't you say that's the square root of u, and what's u? 1 plus x squared, and there's no need to do all of this mess. That works. Another integral I want to get out of the way for you guys, if I was to look at this integral, in case you were wondering how this worked, wouldn't you say, let x equal a the tan of theta? And I know what you're thinking. You're thinking, wait a minute, but this doesn't have a radical. Well, guess what? It turns out 7.3 applies to any problem that looks like this. Any problem. dx is a the secant square root of theta d theta. This becomes the integral. And let me get this out of the way. This becomes the integral of, and let's see how this works. This, oops, not that. This is right there. And this is right there. So isn't that a secant of square root of theta d theta divided by a squared plus, and wouldn't that be a squared tan squared of theta? Basically just substituting everything's value, and wouldn't you say this is the integral of a secant squared of theta d theta over, can't I factor an a squared out? Wouldn't this become a secant squared of theta d secant squared of theta d theta divided by a squared? Isn't that secant squared? And wouldn't that be simply 1 over a the integral of d theta? Isn't that 1 over a times theta plus c? And what's theta? If I have x over a equal tan of theta, isn't theta the inverse tangent of x over a? instead of deriving this every single time, it's worth memorizing. And it's not going away because of this substitution. We're going to be dealing with this a lot more than we like. I suggest you get it out of the way and make your peace with it. And I'm going to derive one more for you. Another example. If I integrate dx over 1 plus x squared, again, we know that's inverse tangent. Let x equal tan of theta. Dx is secant squared of theta d theta. So this is the integral of 1 plus tangent squared of theta, and dx is secant squared of theta d theta. This is quick. So that's the integral of secant squared of theta over 1 plus tangent is secant squared of theta d theta. That is the integral of d theta, which is theta plus c, and the same deal. If tan of theta equal x, then theta equal the inverse tangent of x plus c. That's from Trig. Those arise a lot more than we like, which is why I really needed to memorize them. Let's get one more problem in there, and let's shift this a bit down. We'll play with it in a minute. Did it move or did it not move? Oops, where'd it go? Okay, let's undo that. That's fine. Okay, now let's look at this problem. What if you have this problem? Again, getting rid of a radical is a lot more challenging than we think. So what we need to do, we need to make this matching a square root of a number and a squared. I go on the side and I say, well, that is negative x squared plus x. I'm going to complete the square. To complete the square, the leading coefficient must be a positive number. So I'm going to add a number right there, and I'm going to subtract that number right there. Since that number is multiplied by a negative, I need to multiply this by a negative to keep this balanced. So either you add the same quantity to both sides of the equation, or you add and subtract from the same side. Take half of the middle number, which is 1/2, and square it. So this becomes negative a perfect squared x minus the number before you squared it, plus 1/4. So if I really glance at how this looks, this is really the integral from 0 to 1, the square root of 1/4 minus x minus 1/2 squared. Now, if this is a definite integral, I am in good luck because I don't need that triangle anymore. And in this case, do you see what's taking the place of x? Instead of saying let x, do you see what you're squaring? We're matching this with the square root of a squared minus x squared. It says let x. We're going to let x minus 1/2 because that took the place of x. Let x minus 1/2 equal, what do you square to get 1/4? 1/2. And if it was a squared minus sine squared minus x squared, we let it be sine of theta. Look at the table that's provided. And if I take dx, dx would be 1/2 the cosine of theta d theta. And now if I go in and I change the limits on the integral, the good news, I don't have to use that triangle anymore. This is 1/4 minus, and if I squared this, wouldn't that be 1/4 sine squared of theta? And isn't dx one-half cosine of theta d theta? Now let's look at this and figure out how this works. If I take x equals 0, because that's x equals 0, if I put 0 right there, do you see that I'll get negative 1/2 equal 1/2 sine of x, which means sine of x equal negative 1/2. And where does sine of x equal negative 1/2? Wouldn't that be from negative pi over 2? What if I put a 1 right there? Wouldn't that be 1 minus 1/2, which is 1/2? If I divide by 1/2, I'm getting the sine of x equal 1. The beauty of this, I don't need to go back to the triangle anymore. Now, if I play with this integral from negative pi over 2 to pi over 2, let me see what happens. Here, I could factor out a 1/4, Isn't that 1/4 the cosine squared of theta? Wouldn't that be 1/2 the cosine of theta times 1/2 the cosine of theta d theta? And wouldn't that become the integral from negative pi over 2 to pi over 2 of 1/4 the cosine squared of theta d theta? And again, we know how to do this because we just did in the previous section. Oops. The integral, that's 1 plus the cosine of 2 theta divided by 2 d theta. That is 1/8 times theta plus the sine of 2 theta divided by 2. Right? That is 1/8 times theta. Actually, I don't need to even expand that because I'm running this from negative pi over 2 to pi over 2. That will be 1/8. Plug the pi over 2 in. If you put pi over 2 in there, 2 times pi over 2 is pi, sine of pi is negative, is 0, minus, if I put a negative pi over 2 in there, that's sine of negative pi, which is 0. Now on a test, this is a fine answer to match it at the back of the book. That's 1/8 into pi over 2 plus pi over 2. That is 1/8. Pi over 2 plus pi over 2 is simply pi, so the answer is pi eighths. And there's my homework for this section.